Hey everyone, we're going to learn about the fundamental theorem of calculus. Sounds important, right? So the first thing we need to talk about is what we've already done. So we have already learned how to find the area of something like this, right, using geometry. So we just used the fact that this is a trapezoid. We found the area, right? So here we would just average our bases. So here's a base of 3. This is a base of 5 with a width of 2. Average those. 4 times 2 is 8. Okay, so I could find this definite area. Right? We also learned how to find the antiderivative, like the original function. Right? So the original function, if this was the derivative, would be like 1/2 x squared plus x plus c. All right, so we've already learned how to do that. Okay, so now if we take what we already know and we kind of play with it a little bit. All right, so this is my original function, right? So if I plug 2 in and I plug 4 in, let's just see what happens. All right, so if I plug 2 in to my original function, then I will get 2 squared is 4, divided by 2 is 2, plus 2 plus c, so I get c plus 4. Right, now if I plug 4 into my original function, 4 squared is 16, divided by 2 is 8, plus 4 plus c, that's c plus 12. All right, now if I just notice, if I subtract these, then I get 8, right? Which we already determined was the area between 2 and 4. So, interesting. And that's a rule. Right, that'll always work out. That is the fundamental theorem of calculus. And so first, let's just talk about the rule. So if I take the integral of f prime, I'll get my original function, and I'll plug in my upper bound and subtract my lower bound. That's definitely supposed to be an a. Okay, so the fundamental theorem says the integral from a to b of f prime of x is equal to f of b minus f of a. All right, let's practice that here. So I take the integral of 3x squared, that was just x cubed, from 1 to 2. Right, so this notation here just is kind of an extension of my integral notation here, except I already evaluated the integral, so this squiggly has to go away. I just replace it with a bracket. Or you could do a straight line, either one. All right, so that means it's 2 cubed minus 1 cubed. 8 minus 1 is 7. All right, let's practice now. Okay, so our first step was just to take the integral. All right, so here we're going to have 1/3 x cubed plus 3x, right, evaluated from 1 to 2. So that means I'm going to plug 2 in and cubed it. Plug 2 in and subtract the same thing, but when I plug 1 in. Right, and so we just have to do a little bit of math here. So I have 2 cubed, that's 8/3, plus 6 minus 1/3 and then minus 3. We end up getting 16/3. All right, same deal. What I'm going to do is divide both of these. So if you're kind of confused what I mean by that, just remember that if you have a fraction, you can split it like so. And then I just divide. So 1/9, x divided by x squared is going to be x to the 1/2. And then 4 over x to the square root of x, I should say, is 4x to the negative 1/2 with respect to x. All right, so we're going to take the integral. So I get 2/3 x to the 3/2. And then here it's going to be minus 8x to the 1/2. All right, and if you're wondering how I did that, I just realized 8 times 1/2 is going to be 4, because I know that's just how I think about it. I think about it as when I take the derivative of my answer, how am I going to get 4? Okay, and I'm evaluating from 1 to 9. So like I said, you can do a straight line or a bracket. Either way works. Now you just plug in the 9. So again, we have 2/3 times 9 to the 3/2. minus 8 times 9 to the 1/2 minus, and then I'm going to plug in 1. And if I plug in 1, those exponents don't really matter. You do all the simplification, you'll get 4/3 to be your final answer. All right, next one here, pretty simple. Just remember, if you remember the derivative of tangent is secant squared, it works the same way backwards. So the integral of secant squared is going to be tangent from 0 to pi over 4. So I need to evaluate tangent of pi over 4, tangent of 0. So that's 1 minus 0, or just 1. All right, pretty straightforward. All right, last one on this page. We have absolute value. And so there's a couple ways we can do this. We can do it analytically and we can do it geometrically. It's much easier to do it geometrically. So remember that really it matters where this is centered. Okay, this is going to be centered at 1/2. Okay, because if you set this equal to 0 and you find the x-intercept, that's where it's centered. It's centered at 1/2. Okay, that's essentially where this changes slope. So I know that it'll go down to 1/2 and then it'll rise after that. Right, and I want the integral from 0 to 3. Right, so I'm looking for kind of this region right here. Well, I can split this up. So I know that this is going to be negative 2x plus 1 anytime x is less than 1/2. Right? And I know it's going to be positive 2x minus 1 anytime x is greater than 1/2. So that's where the split is, and you just multiply it by negative 1 to get this one here. Right? So I know I have a slope of negative 2, it's going down until 1/2, and then it's going up after 1/2. Okay, so we could find this area geometrically. Okay, so I have a base of 1/2, and then I have a height of 1 here, and so you could add those areas together. But we can find this analytically, so let's practice that. So between 0 and 1/2, I'm going to be using my function here. So you can treat this like a piecewise function. Right, so I have negative 2x plus 1 with respect to x, plus the integral from 1/2 to 3 of 2x minus 1 with respect to x. Right, we can take these integrals. So I'll have negative x squared plus x from 0 to 1/2. And then I'll have positive x squared minus x from 1/2 to 3. All right, and we're going to plug in these fractions here and plug in these numbers. So I'll have negative 1/4 plus 1/2. Okay, minus 0. So I plugged in 1/2, I got this stuff. I plugged in 0, I got 0. Plus, now I'm going to plug in 3, so I'll have 9 minus 3. And then I'm going to plug in 1/2, and remember you subtract these. So we have 1/4 minus 1/2. All right, you do all the math, you'll get 13 halves out of that. All right, so let's keep going. Now, we cannot do this one analytically. Sorry, we cannot do this one geometrically. We can do this analytically, and it'll work the same way. So I know that this is a parabola shifted down 4 normally, but I know that this cannot exist below the x-axis. So there's a couple ways I can think about this. Right, so if I took my original parabola, right, this is what it would look like. It would intersect at negative 2 and positive 2. But all this stuff cannot exist here because it's absolute value. So I could think about it as just reflecting across, well, it's the worst thing ever. Okay, I could think about this as just reflecting across the x-axis, and this is gone. Oops. And so I'm just left with this graph. Right? Or I could think about it as whatever would be negative is now positive, so I do it the other way. I kind of like to think about it as reflecting. However you get about it, you get a W. Okay. So it works pretty much the same way here. I know that I have my original parabola. So I have x squared minus 4 whenever x is less than negative 2 and x is greater than positive 2, right? So that's my original parabola. Right, now that I know that I have negative x squared plus 4, so that's my upside down parabola, right, whenever x is between negative 2 and 2. All right, so that's kind of the situation that I have. And so if I want to take this integral, I want to know what's going on from negative 1 to 3. All right, so that is all this stuff. Okay, so between negative 1 and 2, I know I'm using the upside down part. So that's going to be negative x squared plus 4. And then from 2 to 3, I'm using the regular part of my parabola. So that's going to be x squared minus 4. Right, and so same process, we're going to take the integral. So it's going to be negative 1/3 x cubed plus 4x from negative 1 to 2. And then positive 1/3 x cubed minus 4x from 2 to 3. Right, we just plug in our numbers, do the first fundamental theorem. You end up getting 17 and then 17/3, which will turn into 34/3. All right, one more example. Right, I want to find the area bounded by all this stuff. This is a very common way of wording this. All this means is that I have some like parabola and I want to know what's going on between 0 and 2. Okay, so it says it's bounded by the x-axis. That's kind of an assumption. That's a given whenever I do an integral. And so the vertical lines here, in this case, my x's are my bounds. Okay, the y is my function with respect to x. Okay, so same thing. I have 2/3 x cubed minus 3/2 x squared plus 2x from 0 to 2. All right, so I'll have 16/3 minus 6 plus 4, and so we get 10/3 at the very end of it. All right, now a common question that I get is why we don't have to include a plus c here, and so I'm just going to address that now. If you're good, then you don't have to watch this. But we can totally do that. So if we include a plus c, just keep in mind that when we do this math here, we're going to plug in a 2 and then subtract that, and we're going to plug in a 0 and subtract that. And so when I plug in 2, I get a whole bunch of numbers. I'll end up getting, I believe, uh, 16/3 minus 6 plus 4, and then I'll have like a plus c here. All right, so this is when I plugged in 2. Now if I plug in 0, I'll get a bunch of zeros and then a plus c there. All right, these c's are the same. So when I do this subtraction here, I have c minus c. Those c's will cancel, and I'm just left with my numbers. So I'm just left with 10/3 anyway. So you do not have to include this plus c because it will cancel itself out. Right, that's it. See you later.